All right, so in this video, this will be the last video on the lecture on energy balances and CSTRs, and I want to talk about how changes in the reactor temperature influence the reactor temperature. So think about a CSTR, and it's operating at some steady state condition, but something happens to cause the reactor temperature, so the T, to change. So this could be the feed temperature changes. This could be the cooling system for a second fails. This could be, for example, if there isn't perfect mixing, if one piece of the reactor starts react, or the rate in one part of the reactor starts moving faster for some reason, so you get a faster rate and hence more heat being given off that eventually spreads around to the rest of the reactor and causes the reactor fluid temperature to go up. So think of any possible thing that could happen that would cause the reactor temperature to rise. So let's pretend that we're sitting at this point. This is where we're operating, and that happens. So the reactor temperature increases a little bit. So for whatever reason. So the reactor temperature is going to increase, so we're going to follow this S-curve up until the new temperature. So say the new temperature, we were originally operating here, which is about 325 degrees or something like that, 330. And now the reactor increases to, let's say, 340 degrees. So for whatever reason, that reactor temperature increases. As long as the cooling system is operating the same and the feed temperature isn't same, so is the same as it was. So this is still our R of T line. When that heat, or when the reactor temperature increases, the R of T, the heat removed, is still greater than the G of T, the heat generated. So the R of T is going to accommodate this, or overcompensate for this change in the reactor temperature, and it's going to cause the reactor temperature to fall back down. So recall that when they look at these curves, points of intersection are the steady state solutions. So if for a moment we break out of the steady state solution, what is going to happen next depends on how the reactor and cooling system are performing. So in this case, something happens to break the steady state solution, raise the temperature of the reactor, but the heat removal term in that case is going to be the cooling system is removing more heat than the reaction is generating. Henceforth, the temperature is going to fall back down, and this is where it's going to land. So it's going to go back to the steady state. Because of that, we call this a stable steady state. Similarly, if we were operating at this point here, and something happened to cause the reactor temperature to increase, at that point, you can't see it because the axis is cut off here, but the R of T line is still greater than the G of T line. Henceforth, the cooling system is going to kick in at this point, and it's going to cause the temperature to decrease back to its original value. Now, we mentioned before that points along this portion of the G of T curve are unstable, and here's what I mean by that. If we're operating at this point and something happens to increase the reactor temperature, so we'll follow this line. So we break steady state temporarily and we start following this line. Now the cooling system is not removing enough heat. So the R of T term, or the R of T trend, is below the G of T trend. So the cooling system cannot account for the amount of heat that's being given off to the reaction. So henceforth, the temperature will continue to rise until we get up to here. In this case, the temperature is going to increase up to this point. So because of this, in this case, where a small change in the reactor temperature caused the reactor to start operating at a new set of conditions. So it's now operating in a new conversion and operating at a new temperature. And that's why we call this an unstable steady state. At these steady states, when there was a small change in the reactor temperature, the heat removal term was greater than the heat generated term. That caused the temperature to fall back down to its original operating point. So that's another reason to think about the solution to design equations for CSTRs or non-isothermal CSTRs using graphical methods, because then we can see where all the steady states are. So we wouldn't necessarily be able to do that if we were using, if we're doing this by hand, or maybe using the goal seek function. The graphical method shows us where the steady states are. It shows us where the ignition and extinction temperatures are. It shows us where the regions where we'll have multiple steady states. It shows us where those steady states are unstable and stable. So it's a useful method for thinking about what happens in a CSTR. One final thing to say about this, this curve only tells you the steady state solutions. So we can think about what would happen outside of steady state, but this curve only allows us to think about that from a hypothetical standpoint. If we wanted to look at non-steady state behavior or reaction runaway, we'd actually have to model that. And we're going to get into that in actually just a little bit in this course.